This will be video 1 for section 4.6 homework on related rates. Number 1 says write an equation that relates dA dt to dr dt. So we have the area equation, and so it's asking me in maybe subtle terms to take the derivative of this with respect to t. So the derivative of a with respect to t is simply the derivative of a with respect to t. So dA dt equals, now I have a constant multiple rule. So I'm going to bring the 2 down. I'm ignoring the constant pi, which gives me 2 pi r. So the 2 came down, r to the first power, and now I need to multiply by the derivative of r with respect to t. And that's it. So I've related the derivative of the area to the derivative of the radius. Number 2 says pretty much do the same thing. Write an equation that relates ds dt to dr dt. So the surface area of a sphere is given by 4 pi r squared. So the derivative of this with respect to time gives me ds dt equals, again ignoring the 4 pi, just focusing on the r squared. The 2 comes down, making it 8 pi r to the first, and then I take the derivative of the radius, which is simply dr dt. And that's it. Question 3 says, part A, how is dv dt related to dh dt if r is a constant? So for the sake of this problem, r is just like the number 2 or 3. We're not taking the derivative of it. It's a constant. So we have the pi r squared as a constant. So this is just the constant multiple rule. So the derivative of v with respect to time is dv dt. The derivative of the right side is the constant multiple rule says ignore the constant and take the derivative of the function. So the derivative of h is dh dt. So I get simply pi r squared dh dt. Really, it's no different than if I had given you the equation volume equals like 5h and asked you to take the derivative of that with respect to time. We would ignore the 5 and just take the derivative of h. So that's what we've done. Ignored the pi r squared and then multiplied by the derivative. So part B says do the same thing, but this time h is a constant. So for all practical purposes, I'm going to view this question now as saying v equals pi h r squared, just to make it easier. So again, the pi h is a constant, and so really all I'm doing is I'm going to take the derivative of the left side with respect to time, and then the derivative of this is really just the derivative of the r squared times the constant. So 2 comes down, giving me 2 pi h r to the first power times the derivative of r with respect to time. And that's it. And then part C says neither one are constant. So now I actually have an r squared and an h being multiplied by each other, and then the pi is the only constant. So product rule would be in order. So I will group pi with r squared and treat that as function 1, and then function 2 is h. So the derivative of the left is dv dt equals the derivative of the first term, or the first factor I should say, is 2 pi r dr dt times the second function plus the first function times the derivative of the second. So just dh dt. And that's it. All right, moving on to number 6. We've got area of a triangle using a little bit of trigonometry here, and they give us the equation. And now it says, how is dA dt related to d little a, dB, and d theta dt? So none of the variables are going to be treated as constants. So what I really have here is what appears to be a triple product rule. Okay, so let's just dig into it. The derivative of the left side is dA dt. And for this triple product, I think it's just going to be easier to take the 1/2 and really just completely ignore it. So constant multiple rule, the derivative of all of this times the constant. So let's take the 1/2 down, and now we can basically just ignore the 1/2. Okay. So now I got to do a triple product rule. And so I'm going to treat the AB as the first function and sine of theta as the second function. So the derivative of the first function AB is in itself a product rule. So the derivative of A is dA dt times B plus A times the derivative of B with respect to time. Alright, so there's the derivative of the first times the second plus the first times the derivative of the second, and all of that is going to be multiplied by, now thinking about this, this is the first function and here's its derivative, so there's the derivative of the first times the second, plus the first times the derivative of the second. The derivative of sine of theta is going to be cosine of theta, but then we're going to have to deal with the theta, which is embedded, so times d theta dt. I could distribute the sine to both of these terms. I could distribute the half to every term, but essentially this is my answer. Alright, number 10. We have a rectangular box and it is changing in size. The edges x, y, and z are changing at the following rates, and so I've already written those down. dx dt is growing by 1 meter a second, dy dt is shrinking by 2 meters per second, and dz dt is growing by 1. So the box is in motion, and it says find the rates at which the box is, for A, the volume is changing. So that means I'm just going to write volume equals, and then just the equation for the volume of a box, which by my dimensions here would be x, y, z. And they want me to find the rate of change of the volume, and that tells me that I want to take the derivative with respect to time. How is volume changing over time? And again, just like the last problem, I have a triple product rule. So the derivative of the volume with respect to time equals, I'll treat these two as the first function and this guy as the second. So calculus tells me for the product rule that the derivative of the first one times the second. So now I got to do a product rule within it. So the derivative of x with respect to time is dx dt times the second one plus the first times the derivative of the second. All of that is simply the derivative of the first times the second, just the second, plus x, y, dz dt. And this time they actually want me to find dv dt, not just write an equation that relates it. So I'm now going to plug in the information that I have. The box is changing, and so the snapshot time that they want us to take a look at this is when the x, y, and z are 4, 3, and 2. So now I'm just going to plug in what I know. dx dt is 1 times y, which is 3, plus x, which is 4, dy dt, or dy dt, oh I wrote an x, that's supposed to be a t. This is a t here, sorry about that. Okay, so that's dy dt, yeah, -2, times z, which is 2, plus x, 4, times 3, times dz dt is 1. So it looks like we have 3 minus 8 times 2 plus 12. Or dv dt equals 3 minus 8 is -5. -5 times 2 is -10. Plus 12 is 2 meters. It's volume, meters cubed per second. So some of them growing, some of them shrinking. The overall result is a volume change of 2 meters cubed per second. At least that's what I got. Alright, so essentially we're going to do the same thing on part B, except now we're going to be looking at surface area. And the surface area, I'm just going to call it A, but it is surface area, would be the area of all the blocks, or all the squares, rectangles. And so we have, the area would be 2 x times y's plus 2 x times z's plus 2, what am I missing? Z times y's. Alright, that should do it. So now the derivative of the surface area with respect to time. And I have, I'm going to run out of room. We have 3 product rules, but they're easy product rules. So I get 2 dx dt y plus 2x dy dt. Yep, diagonal's got no room. So that's all the first one. So I got to do it again. Plus 2 dx dt times z plus 2x dz dt. So all of this is the derivative of that term. And I've got one more. So plus 2z becomes 2 dz dt times y. So product rule, first, second, times, or sorry, plus the first times the derivative of the second. And that should be my derivative. Now I would just plug in all the information and solve for dA dt. So let's see if we do this real quick. I've got 2 times dx dt, which is 1 times y, which is 3, plus 2x dy dt, plus 2 dx dt, z, plus 2, x is 4, dz dt is 1, plus 2, dz dt is 1, y is 3, plus 2 times -2 So that equals 6 minus, let's see, 16 plus 4 plus 8 plus 6 minus 8. So minus 8 plus 8, 6, that's a 4. So 6 and 6 is 12, plus 4 is 16, minus 16 equals 0. So it's changing at 0 meters squared, because it's area per second. So the end result is my surface area actually is not changing at all based on the rates of change of the 3 sides. So let's jump down and maybe take a brief look at part C. The derivative is going to be a little obnoxious. One option, if you don't want to do the chain rule with the square root, is we could actually square both sides of this and then take the derivative of s squared equals all of those squared. And that would be a lot easier than what we're about to, if we just did it as a chain rule. Chain rule, we'd have to have a 1/2, all this stuff to the negative 1/2, so now the square root's in the bottom. I think it'd be easier just to think of it as s squared equals x squared plus y squared plus z squared. So we'd get 2s ds dt equals 2x dx dt plus 2y dy dt plus 2z dz dt. Now we can plug everything in I know and solve for ds dt. Okay, I'm going to stop this video here at 16 minutes, and we'll pick it up on number 11 with the next one.